Here's your text, punctuated for clarity and flow. Pluto is a distant and mysterious dwarf planet, which was once a member of our solar system's planetary family. However, recent startling announcements by leading astrophysicist Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with shocking revelation. They suggest that this icy world is on a potential collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there something more to this impending cosmic collision? Join us as we explore the possibilities of a Pluto-Neptune impact. Pluto, a former planet that was demoted to a dwarf planet partly due to its peculiar orbit, remains a subject of fascination and study in the astronomical community. According to recent predictions by leading scientists, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the red flag about a possible hazardous collision between these two planets that could pose a huge threat to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even finished one full revolution. But the intrigue doesn't stop there. Pluto's path is marked by its highly elliptical shape, deviating significantly from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its inclination, angled at 17 degrees to the ecliptic plane. The path Pluto traces is much steeper compared to the other planets. This inclination and elliptical nature add layers of complexity to its orbital pattern. One of the most intriguing aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the solar system. This leads to the natural question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand its unique trajectory. Unlike the other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep incline and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is a testament to the intricacies of space mechanics. The three-body problem in space is about figuring out how three celestial bodies, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict their movements based on their starting positions and the gravitational forces they exert on one another. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all interact in a complex way. The terms azimuthal libration and latitude libration, along with the VZK oscillation, are part of this puzzle. So, why don't Pluto and Neptune collide? According to astrophysicists, what keeps all planets in their orbits is azimuthal libration. In the context of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in preventing a collision. Latitude libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is situated significantly above their orbital plane, providing an additional layer of protection from potential collisions. Another crucial component in this equation is the VZK oscillation, named after three scientists, von Zeipel, Kozai, and Litov, who studied how celestial objects move in space. This phenomenon explains how three bodies, such as Pluto, Neptune, and the Sun, pull on each other gravitationally, influencing their orbits over long periods. Even though Pluto's path seems unpredictable, this oscillation helps keep it moving smoothly over time. The VZK oscillation shows that even if things in space appear chaotic, underlying patterns and rules help maintain order. All of these factors work together to keep Pluto's orbit stable, ensuring that it does not crash into Neptune or get thrown off course. The role of other planets in Pluto's stability. Numerical simulations in the late 1980s revealed that, despite its stable properties, Pluto's orbit is technically chaotic. Minor deviations in initial conditions could lead to significant differences over millions of years. However, these unique properties of Pluto's orbit maintain stability over incredibly long timescales, effectively keeping chaos at bay. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Neptune's gravitational influence helps keep Pluto in a stable resonance. Every time Pluto completes 2 orbits around the Sun, Neptune completes 3. This 2:3 resonance prevents collisions. Jupiter's gravity is strong enough to further stabilize Pluto's orbit, ensuring it remains on a predictable path for billions of years. Saturn also plays a minor stabilizing role in this system. These planetary interactions work together to keep Pluto moving safely through space without running into trouble. Is a Pluto-Neptune collision possible? For the foreseeable future, Pluto and Neptune's orbits remain stable due to their mean motion resonance and various gravitational influences. A direct collision is highly unlikely. However, the complexities of orbital dynamics mean that astronomers must continue to monitor these celestial bodies to better understand their long-term behaviors and potential risks. While the scenario of a Pluto-Neptune collision is largely speculative and improbable with our current understanding, it underscores the importance of continuous research and observation in astronomy. Advances in technology, such as improved telescopes and computer simulations, will allow astronomers to refine their models and predictions, ensuring we stay informed about the ever-changing nature of our solar system. Perspectives from Neil deGrasse Tyson and Michio Kaku. Neil deGrasse Tyson, a prominent astrophysicist, played a key role in Pluto's reclassification from a planet to a dwarf planet. He argues that this was not a demotion, but an adaptation to our expanding knowledge of celestial bodies. Tyson views Pluto's complex orbit as a reminder of how much there is still to discover in space. Michio Kaku, a renowned physicist and futurist, offers a complementary perspective. He focuses on the unpredictable forces that shape our universe and emphasizes the need for continuous observation and advanced modeling. Kaku sees the interactions between celestial bodies as crucial not just for academic curiosity, but for practical implications, including space exploration and planetary defense. Both Tyson and Kaku agree that space remains a realm of endless discovery. They emphasize the need for continuous exploration, advanced modeling, and an evolving understanding of celestial mechanics.